Have you ever wondered how digital systems evaluate logical expressions? Well, let me introduce you to a tool that plays a key role in this process: the truth table. A truth table is a tabular representation that succinctly illustrates all possible combinations of input values for a Boolean function and their corresponding output values. It's like a map for logical expressions, guiding us through the landscape of all possible outcomes. Now let's break down the components of a truth table. Imagine it as a table with several columns and rows. The input columns, each representing an input variable or signal, form the backbone of the truth table. The number of these columns directly corresponds to the number of input variables. Then we have the output column. This lone ranger represents the output variable or the result of the Boolean function. But what about the rows, you ask? Well, each row is a unique combination of input values. Think of it as a different scenario or situation that the logical expression could encounter. So together, these components paint a comprehensive picture of how a Boolean function behaves under all possible input conditions. But how do we fill in this table, you wonder? First, we determine the number of inputs, then we list all possible combinations of zeros and ones for these input variables. Remember, for every input variables, there will be 2 raised to the power and rows in the truth table. Then comes the fun part. We evaluate the Boolean expression for each combination of input values to find the corresponding output value. It's like solving a puzzle, isn't it? Finally, we fill in the truth table with the input combinations and their corresponding output values. And voila! We have our truth table. So, truth tables are crucial in understanding and interpreting the behavior of a Boolean expression. They are the unsung heroes in the world of digital logic design, Boolean algebra, and the analysis of combinational circuits, helping us navigate the complex world of digital systems with ease. Now that we know what a truth table is, how about we delve into creating one? Creating a truth table isn't as daunting as it may seem, especially if you follow these simple steps. First off, we need to identify the number of inputs. Each input variable or signal for your Boolean function will be represented by a column in your truth table. So if you have 3 input variables, you'll have 3 columns for the inputs. Next, we need to list all possible combinations of these inputs. This is where things get a bit binary. We use zeros and ones to represent the possible states of our inputs. So for n input variables, we'll have 2 raised to the power of n rows in the truth table. For example, if we have 2 inputs, we'll have 4 possible combinations: 0, 0, 0, 1, 1, 0, and 1, 1. Once we have our inputs and their possible combinations, we move on to the fun part, evaluating the Boolean expression. This is where we apply our Boolean function to each combination of input values. For example, if our Boolean function is AND, then our output is 1 only if both our inputs are 1. Otherwise, it's 0. Now we're ready to fill in our truth table. We list our input combinations in the input columns and their corresponding output values in the output column. If you've followed along so far, you'll see that the truth table neatly organizes all the possible combinations of inputs and their resulting outputs. But wait, there's more. Sometimes our Boolean functions can get a bit complex, involving more than one operation. In such cases, it helps to break down the expression and evaluate it step by step. We can add additional columns to our truth table for intermediate results. For instance, consider a Boolean function where we're ORing the AND of 2 inputs with the AND of their inverses. We start by evaluating the AND operations first, one for the inputs and another for their inverses. We then OR the results to get our final output. Each of these steps can be represented by a separate column in our truth table. This step-by-step approach not only simplifies the process, but also provides a clear picture of how the Boolean function is working. It's like having a roadmap for your Boolean expression. Once you've filled in all the columns, take a moment to review your truth table. Ensure that you've covered all possible input combinations and correctly evaluated the outputs. If everything checks out, congratulations! You've successfully created a truth table. And voila! You have your truth table. It's as simple as that. Remember, practice makes perfect. The more truth tables you create, the more comfortable you'll become with the process. So keep practicing, and you'll be a truth table pro in no time. To better understand, consider the Boolean expression FAB, AB plus AB. This is a typical example of a Boolean function consisting of 2 variables, a and b. We will now create a truth table for this expression. In the first step, we identify the number of input variables, which in this case are 2, A and B. Therefore, we will have 2 columns for these input variables in our truth table. Next, we generate all possible combinations of 0 and 1 for these input variables. For 2 input variables, there will be 4 rows in the truth table. We start with 0, 0, then 0, 1, 1, 0, and finally 1, 1. Now we evaluate the Boolean expression for each combination of input values. Here's how it works. For the first combination 0, 0, both parts of our Boolean expression are 0 because anything multiplied by 0 is 0. Hence, the output is 0. For the second combination 0, 1, the first part of our expression is 0 because A is 0, but the second part is 1 because we are multiplying 0, which is the negation of A, with 1, which is B. Therefore, the output is 1. For the third combination 1, 0, the first part of our expression is 0 because B is 0, but the second part is 1 because we are multiplying 1, which is A, with 1, which is the negation of B. Therefore, the output is 1. Finally, for the last combination 1, 1, both parts of our expression are 0 because we are multiplying 1 with 0 in both parts. Hence, the output is 0. After evaluating the Boolean expression, we fill in the truth table with the input combinations and their corresponding output values. This example should give you a clear idea of how to construct and interpret a truth table. Remember, a truth table provides a clear understanding of how a Boolean expression behaves for all possible input combinations. It's a valuable tool in the analysis and design of digital systems. So we know what truth tables are and how to create them, but why are they so important? Let's delve into the significance of truth tables in different aspects of digital logic design and beyond. First, truth tables are fundamental in logic design. When designing digital circuits, truth tables serve as blueprints, guiding us on how the circuit should behave for every possible input combination. They help us understand the relationship between the inputs and the outputs of a Boolean function, making it easier to design a circuit that performs that function. Additionally, truth tables are invaluable in debugging digital systems. Imagine you've got a complex digital circuit and it's not behaving as expected. By comparing the output of the circuit with the expected output from the truth table, we can identify where the logic is going wrong. It's like having a roadmap that helps us troubleshoot and rectify any inconsistencies in our logic circuits. But it's not just about design and debugging. Truth tables also promote a functional understanding of Boolean expressions. They provide a clear tabular representation of how a Boolean expression behaves for all possible input combinations. This makes them a fantastic tool for learning and teaching digital logic and Boolean algebra. Truth tables also lend themselves to further mathematical analysis. They provide the basis for simplifying Boolean expressions using methods like the Carnot map or Quine-McCluskey algorithm. In essence, truth tables are a bridge between theoretical logic and its practical application. They translate abstract Boolean expressions into a practical, easy-to-understand format that can be directly applied to the design and analysis of digital systems. Truth tables are a testament to the beauty of logic and its application in the digital world. They embody the simplicity and elegance of Boolean algebra and digital logic design, turning abstract concepts into tangible, usable technology. With truth tables, we can systematically analyze and design digital systems, making them an invaluable tool in the field of digital logic design. In a nutshell, truth tables are the backbone of digital logic design. They provide a systematic approach to mapping out all possible combinations of input values and their corresponding output values for a Boolean function. A truth table is comprised of columns representing the input variables and one column for the output variable. Each row is a unique combination of input values. Creating a truth table involves identifying the number of input variables, generating all possible combinations of these inputs, evaluating the Boolean expression for each combination, and finally filling in the truth table. They serve as a critical tool in designing and debugging digital circuits and understanding the functional behavior of Boolean expressions. Now that you know the basics, I encourage you to practice creating your own truth tables for different Boolean expressions. It's the best way to solidify your understanding. Remember, practice makes perfect, so grab a pen and start creating your truth tables. Until next time.